Day 31 Physics, Newton's second law. It's usually expressed like this in equation form, mathematical form. This is really pretty much the only one of the three laws of motion, Newton's laws of motion, that is in mathematical form. As we remember, the first law was the law of inertia. An object at rest stays at rest. An object in motion stays in motion in a straight line unless acted on by an unbalanced force. And then we have Newton's second law, F net equals ma, and basically F net is the unbalanced force that causes acceleration. So F net, F sub net, is net force measured in newtons. That would be our standard unit, capital N. You could do it in pounds. That would be the English unit. We're not going to use pounds. As you might recall from a previous page, 1 pound, if you have pounds, you want to convert to newtons. 1 pound is 4.45 newtons. There's a point, decimal point right there. So you'll have to convert to newtons to use this in standard form. So net force is the combination of all forces that are acting on an object. If there's only one force acting on an object, that single force is the net force. That happens quite often. But the way you figure out the net force is like we did last unit. It's the sum of all the vector forces on an object. I'll do a couple examples here in a few minutes. But it's important to remember that objects, just because an object experiences a force doesn't mean it accelerates. For example, if you're sitting in a chair, you have at least two forces acting on you. You're sitting in a stationary chair. There's the force of gravity straight down and the force of the chair up on you. Well, if you're just sitting there and motionless relative to the ground, your net force is zero. Even though you have two actual forces applied to you, the net force is zero. So you cannot say force causes acceleration. It's net force that causes acceleration. The key here that we're linking together is a net force and acceleration. Things will accelerate if there's an unbalanced force, a net force. This is kind of a takeoff on the first law. And m is the mass of an object, and we want our mass in kilograms. And then a is the acceleration. Measured in meters per second squared if everything is in standard. So here are things that will, and we want to focus on a constant net force, which will cause a uniform or constant acceleration, so we can still apply our uniform acceleration equations from previous lessons. All right, a couple of example problems for Newton's second law. Once again, I want to emphasize it's not force that causes acceleration. Things can have a force and not be accelerating. What causes acceleration is a net force, and you'll see that in the diagrams here as we go along. It's important to draw the free body force diagrams. Like we practiced yesterday. So here we go. First example, you have a ball falling down, but let's just draw the ball right now. And we know it's falling down towards the earth, but we don't care about the earth right now. We're focusing on the ball. It's a free body force diagram for the ball. So what forces are acting on it? Well, it's the force of gravity down, and now we can actually calculate that, as we saw in class. The equation for force of gravity, W, the weight, force of gravity, equals the mass of an object times g. So the weight of this ball is its mass, 1.5, make sure it's in kilograms, which it is, times 9.8. And if you multiply that, you get 14.7. And I will allow you in class, that's 14.7 newtons, to use 10 instead of 9.8, in which case the weight would be then rounded off to 15 newtons. That's the force of gravity. That will be the force vector pulling down on this ball, 14.7 newtons of force pulling that ball downward, trying to make it accelerate down. Now without air resistance, that would be the net force, but here we have a force of air resistance that impedes the normal falling acceleration rate of 9.8 meters per second squared. And I can show that as if the ball is going down, air resistance is up, but it's 6.2. Now 6.2, I'm going to draw that vector a little shorter, about half as long. Not even half as long, but around half as long as the 14.7, because the 6.2 newtons of air resistance is an upward force. So those are the two forces acting on the ball. And now we're trying to find the acceleration of the ball using F net equals ma. Well, F net is the big force down minus the small force up, so it'll be 14.7. You can probably do that in your head, but I'll write it down here. It's 14.7 minus 6.2 equals the mass of this ball, which is 1.5, times the acceleration. So we'll solve that for A. And in this case, that's 5.7 meters per second squared. When there's no air resistance, the acceleration will be 9.8. Okay, example number 2. We have a ball that's going up and probably slowing down because of gravity and air resistance. So the free body force diagram for problem number 2 is going to look like this. Here's your ball, and we're going to draw the forces. Once again, it's the same ball with the same force of gravity, so it's trying to be pulled down by gravity with a 14.7 Newton force. But as it goes up, traveling up, air resistance is now opposing the motion, and I'll draw that. This is not the way I normally draw it, but it's a short vector. It's still the 6.2 Newton vector down on the ball. So there's two forces being applied to the ball. One's the gravity vector, like always, and then the force of air resistance, which now is down because the ball is traveling up and air pushes against the ball. So now, if you do F net equals ma, it's the vector combination of those two force vectors, but they're going to be additive. In the first problem, one was down, one was up, so essentially when you combine them, you're just like subtracting. Here you're adding, so it will be 14.7 plus 6.2 for the F net equals the mass, 1.5, times A. So the acceleration, in this case, is 13.9 meters per second squared, because there's, in a sense, two things slowing the ball down. One that's in addition to the gravitational force, which would normally cause an acceleration of 9.8 or negative 9.8 meters per second squared. All right, let's do some more examples. A couple more examples of Newton's second law. We have a ball. It's a slightly lighter ball. We have to recalculate the force of gravity, the weight of the ball. W equals mg. And the weight will be the mass, 1.3 kilograms. The units are good. Get them in kilograms if they're not. Times 9.8 meters per second squared. And that comes out to be 12.7. Once again, if you want to, that's newtons. If you want to take 1.3 times 10 and make it go faster, it gives you 13 newtons, rounded off to 2 sig figs. That's what this ball weighs. That's the force of gravity down on the ball. So there's the vector arrow showing you 12.7 newtons of force down. Once again, the ball's falling down, so the force of air resistance is up. I don't know how big that force is in this case. I don't know if it's bigger than, less than, or equal to, but it's probably a little bit less than the 12.7 newtons, most likely. So I'll just draw a smaller vector there to kind of keep these proportional. But I don't know what it is this time. I'm just going to call it F. You could call it F sub R. We don't really need the subscript, but R for air resistance. So in this case, we don't know what that is. All right, so this is a variation of Newton's second law, which is F net equals ma. What is the net force here? Once again, when two vectors are opposed like this, the net force, combining them, is taking the bigger one minus the smaller one. So it'll be, and we're assuming the force of air resistance is smaller than 12.7. 12.7, which it has to be if it's accelerating downward, minus F sub r. equals the mass of the ball, 1.3, times the given acceleration, which is 7.5. So there we have our algebraic equation, and we solve for F sub r. And the force of air resistance comes out to be like 2.9 or 3.0 newtons, depending on how you round off as you go along there. I'll say it's I'll take either answer. They're 2.9 newtons to 2 sig figs. And there we have the force of air resistance. All right, now number 4 is kind of a tough one. It looks very similar, and it is similar, but in the analysis here you're going to find it's a little tougher. We're going to apply the same principles, though. We have a ball that's going up. While it's going up, it's a lot like problem number 2 in the sense that there's two forces acting on the ball. There's the force of gravity down, which is the weight of the ball. You can call it F sub g or you can call it W. And then there's air resistance, which I don't know how big it is. But we do know that the force of air resistance in this case is 4.4 newtons. Straight down. So we're going to apply F net equals ma again. Let's write that down. F net equals ma. Now in this case, when two forces are both in one direction, the net force is the sum of the two. So the net force is W plus 4.4 equals m times 11.8. Now it looks like we have two unknowns here, which we sort of do, except for, if you remember, W equals mg, where g is 9.8. In other words, W equals m times 9.8, or you can switch that around, W equals 9.8 times m. So if we take that, because this is the tricky move here, if we take that and put it in for W, what we have here is 9.8 m plus 4.4 equals 11.8 m. If I reverse using the commutative property of multiplication, 11.8 m. That's 11.8 m there. So if I subtract the 9.8 m from both sides, I get 4.4 equals 11.8 m minus 9.8 m. It's like 11x minus 9x is 2x, or 2.0x, or 2.0 m here, where m is the unknown. And then you divide both sides by 2. So the mass here would be 2.2 standard units kilograms. That's a tough one. But bottom line, F net equals ma. You have to draw your diagram, and not all diagrams will have two forces. Sometimes you'll have 3 forces or 4 forces that you have to combine. We're just starting with problems where there's 2 forces, and we'll show you some other examples later on. But here's some other just quick practice problems for free body diagrams. All right, here are some more just quick examples of free body diagrams. We're not going to calculate anything here, but we're going to get a little bit more particular about our free body diagrams because we want to get the relative size of the vectors. We have a person in an elevator. The person is the important thing, but I'm going to draw my person as just a square to simplify it. That's the person in the elevator. And the person is accelerating up. When you're in an elevator, you have 2 forces acting on you. The floor, anything you're touching, you're standing on a floor here, exerts a force perpendicular to the floor, or upward on you in this case. Well, the other force, though, is the force of gravity straight down. We can call it F sub g, or we can call it W. That's the force of gravity pulling you down towards the earth. But now, this person, which is represented by the square or rectangle, is accelerating upward. Therefore, my up vector, force of the floor, that's the force of the floor or force of the elevator. I'll call it F sub floor, the floor of the elevator. The force of the floor is up on you, and it's bigger than the force of gravity down. So if you did an F net equals ma substitution later on, it would be force of floor minus W to get F net. It's the bigger, how much bigger that force of floor is than the weight that's causing the acceleration. But how about this? There's a person in an elevator accelerating down. The whole system is accelerating down, but we want to concentrate on the person. Here's the person once again. The weight vector will not change. If it's the same person, it's the same weight vector, straight down. Once again, you can call it F sub g for force of gravity, or we have the shorthand W. But if you're accelerating down, once again, you're standing on the floor, but what happens is, and you might have sensed this before if you've ever been in an elevator, when it first starts up and you start to go down from a top floor, you feel light for a second, because what happens is as it accelerates down, that's because the force of the floor is lessening on you and the whole system in a sense, but the one that's on you is the force of the floor. The force of the floor is temporarily smaller than the force of gravity. And once they equalize, you can't change W. W is dependent on the Earth's mass, your mass. That doesn't change. But the system of the elevator with the cables and so forth tied to the elevator, it changes the feeling or the force of the floor exerting on you to cause you to accelerate up or down. Once they equalize, you'll be going at a constant velocity, either up or down, or just being at rest. For example, let's get some more examples. Here I have a fireman sliding down a fireman's pole. We don't care about the pole. Here's the fireman. Just keep it simple. Like all these problems, if you're on Earth, you have a weight vector. Let's say it's the same person, W, or nearly the same person, force of weight pulling you down. As you're sliding down the pole, now, once again, you can think about this in a complicated way. You know, what other forces acting on you? We're ignoring any little small air frictional forces, but really what it is a friction between your hand and the pole. As you slide down the pole and you grip the pole, you can control how hard you grip the pole and how hard the force is between your hand and the pole is. But as you're sliding down, the force of the pole on your hands and or your legs if they're grabbing onto it is up. Now if you're accelerating down the pole, your force vector is small. That's that little vector, and I can put it anywhere in a diagram pointing up. That's the force F sub pole. The force between your hand and the pole, the force on your hands due to friction between the pole and your hands. That's this force of pole up. It's smaller because you have to be accelerating down. The bigger force has to be in the direction of the acceleration. In this case, down. How about this though? Number 8, firemen climbing a pole at constant velocity. Once again, it's because there's friction between your hands, or the fire person's hands. As you'll see a pattern here in all these problems, the weight vector is down, the force of gravity is down. And if you're climbing up, if you want to accelerate up, you need a force bigger than gravity to accelerate up. But if you're just going up at a constant velocity, and once again, it's because of the friction between your hands and a pole, the up vector, and I can draw it anywhere I want, but I'll do it sort of like the last problem. This force right here should be the same length as the weight. I made it a little shorter, so I'll make it a little, try to match that up. That's the force of the pole in this case. The item that's touching your hands, it's due to how hard you're gripping the pole, but you don't need to consider that. It's got to be equal to, that force vector has to equal the weight vector for you to have constant velocity, because if one of those forces is bigger, you will accelerate. Okay, a couple more quick examples here. A car accelerating forward. So now we're not doing a gravity problem. Here's a car. I don't want to draw the wheels, the windows, and everything else. But there's a car accelerating forward, say to the right. Well, I do want to draw, the car does have a weight, a really big weight vector. So I really can't draw this to scale because it's going to be a lot bigger than like the fire person or the person in the elevator. But if the car is going forward on a road, that force isn't going to be that important right now, because what's going to happen is there's going to be an equal force of the road supporting the car up. And those will cancel out because that's not causing the acceleration. What's causing the acceleration is through the engine touching the wheels, there's a forward propelling force. Now, as you go forward, there is a backwards resistance, air resistance and other restricting forces. So if the car is trying to go to the right here, accelerating to the right, there'll be an opposing force, the force of friction, opposing the motion. That's the force of friction. But if you're accelerating to the right, that means the generated force forward, because the engine's running and turning the wheels, there's a forward propelling force I'm going to call it the force of the engine. We'll elaborate on that later on. It's the force due to the engine running and through the transmission, through the tires, hitting the road, and so forth. But there's a forward propelling force that's bigger than the force of friction that opposes the motion. So this will accelerate forward. And finally, airplane. Here's my airplane. So you see a pattern here. Everything is the same. It's an airplane. The airplane's in air at a constant horizontal velocity. It's going to look a lot like the car problem. There's a downward weight vector trying to pull the airplane down to the ground. And there's a upward force, not by a road though, we call it lift. It's the force of lift, L-I-F-T, that has to equal W to keep the plane level. If that force was bigger than the weight, the airplane would start going up, 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 or accelerate up. This keeps the airplane level. But what keeps the airplane going forward? Once again, there's the thrust from the engines, but there's also air resistance, force of friction, air resistance. I'll call it force of friction. I should say friction, I'm out of space there. Force of friction repelling or retarding the airplane, but there's the forward force of thrust. And once again, that force that I just drew there to the right, which is trying to make the airplane go forward to the right, is what we call thrust. Force of thrust or force of engine, T-H-R-U-S-T. Those have to be equal to the force of friction, because if your force of thrust is bigger than your force of friction, the airplane will accelerate forward. If it's less than friction, the airplane will be slowing down. When you have one force beat another force, the object will accelerate. If it's not accelerating, or if it's at rest, all the forces must equalize in those particular directions. So once again, force does not cause acceleration. Net force causes acceleration.